Christos squared, as Maria introduced. Yeah, my name is Christos Katsanos. I'm from the Aristotle University of Thessaloniki in Greece. I'm an assistant professor there in the Department of Informatics. This is actually the result of an MSc thesis in our master's program, which is called, I forgot the timer. Isn't it full screen? Okay. Doesn't seem to work. Where is full screen mode? Okay. Is it better? Yeah. Okay. Thanks. I was talking about our master's program, which is called Technologies of Interactive Systems. This is an MSc thesis in this context that I supervised. So basically, it's the work of Christos Papadopoulos, who unfortunately could not be here due to work issues. So I will present on his behalf a bit of introduction. My animations are not working for some reason. We open the PDF. Did we open? Okay. So it's a bit of introduction, assembly processing, manufacturing environments. The majority of them are performed by robots, and the conventional methods involve programming these some type of programming these robots. For example, typically using a teach pendant. They have various disadvantages. For example, they are time-consuming. They require expertise that is hard to find. Specific programmers for this work. They're not easily adjustable afterwards, and the task may change, etc. So one promising solution to this problem is what's called robot learning from demonstration, or LFD for short. Nothing with LFD. And here the idea is that human instructors teach the robot the tasks that the robot has to do. There are various approaches for this. It sounds good. It has its problems, of course, but two main types of categories are passive LFD methods and active LFD methods, which is my next slide. Passive LFD methods are actually where users interact with the robot and do not interact with the robot directly or through any user interface, and the system tries to understand their actions, for example, computer vision or using tracking for their human motions. And active LFD methods, for example, kinesthetic teaching, is where a user physically moves the hand of the robot or the robot itself to do a task, or remotely controls the robot. So this is actually called teleoperation. They have the exactly opposite advantages and disadvantages. I will cut us some time and not go in there now. And our research motivation is because teaching assembly tasks is still challenging, particularly for small and medium-sized industries, to propose a new LFD method that tries to combine the two approaches, the active and the passive ones. So doesn't require specialized equipment, and tries to combine the advantages of the active LFD methods, which is more accurate and less and more efficient. So in a nutshell, I will go into detail in the following. The user demonstrates the assembly task using a web browser in a 3D simulation environment, and the robotic simulation is simulated. The user or teacher of the task can run the simulation at any time to see if there are any conflicts or any collisions or things that shouldn't happen when the task is transferred to the real robot. So this is a simulated robot who don't care if it does a peculiar movement and destroys itself, for example. So this is basically a simulation environment where the human teacher can perform the LFD method. So these are some screenshots of the tool that was developed by Christos, the other Christos, not me. you can see the numbering. The user enters some assembly info and uploads 3D CAD files, which are typically available for these settings in industries. You can see an example here of our evaluation study, which is the assembling, putting two PC boards on an LCD TV, which is from a real factory setting. Here you can see the teaching user interface, which is actually offers some controls, for example, to move objects, rotate them, and save the current state. This is performed in steps. There are some keyframes that are configured by an administrator of this tool that needs to be filled like a wizard-based procedure. For example, in the first keyframe, you need to move the yellow keyboard to this point, then the second unscrew them or whatever else. And at any time, the user can press the run button. You can see it here and see what is actually done so far. So the robot interpolates, obviously, the movements in the keyframe and performs the action that should be performed. And you can see if it collides or it can place it somewhere else. You can evaluate its accuracy, etc. So there is a lot of coding and technology involved. I will just give you a mental map here. On the front end, we have Angular, which implements the user interface, and a web server, a Node.js web server. We have, of course, the robot operating system and the 3D simulator in Gazebo to simulate the physical components of the assembly space. And in between, we have some Python scripting and libraries that perform the intermediate, exchange JSON files and stuff like that to make it work. Okay. So we also did, in the context of Christos' thesis, an evaluation study with our goal being it's a formative user testing study. Our goal was to evaluate the usability of the proposed approach versus a computer vision system, which is state-of-the-art, let's say, in most cases, for the same assembly task. The assembly task is from a real-world setting. This is a factory in Thessaloniki. This is a picture from there, where currently it is manually done. So our task is the one from operator 1. So the LCD TVs come in the assembly line, and his job is to place two boards on specific places. So the next one can screw them and so on. Okay, so this is the current status. So this is a small industry. So for the methodology, it's a within subjects research design. So all participants experienced both conditions, both the proposed LFT method and the computer vision based one. We involved 25 participants. You can see the distribution, 9 females, 16 males. Some statistics about the age, and they had no robotic expertise, and they were highly experienced computer users in general. The assembly task positioned two PCB boards at the rear of an LCD TV, and as I said, it's a real-world scenario. So the computer vision-based system, the one condition, the other is our system, which is the control condition here, is an existing system in the literature. I would say it's a typical computer vision-based system. It uses a sensor to record people while they are performing the task, and it uses machine learning algorithm to extract the task that should be then given to the robot. So it typically requires a good setup, for example, a robust graphics card, because it can be quite lengthy in terms of time otherwise. And the user has to wait each time, because you can do an error and you might need 3 hours to wait just to correct something. This is not feasible, of course, in a practical setting. So we used a quite good graphic card for our experiment. And this system comes also with a software on a tablet that allows you to start the capturing or see the end result and stuff like that. So other than that, the system just passively, it's a passive LFT method, passively monitors the user. In terms of study procedure, of course, we took in 10%, and then the users saw a brief video of how the task is actually done, and they were asked to physically execute it. We actually had an LCD TV and 2 boards, and they had to put them in a specific places denoted with two papers. The users performed the 2 conditions. Afterwards, the order of presentation was alternated actually for its user to minimize order effects. And at the end, they completed a questionnaire with demographic questions, the system usability scale in Greek, and a binary question of system preference. Which would you prefer? Okay. So usability metrics, we also collected objective metrics, task success, time on task, score, and system preference. These are our dependent variables for this study. Okay. The independent is the teaching method. Now, moving on to the results, we did not find any significant effect of teaching mode. On the left, I will always have the control condition, which is the computer vision-based system, and on the right, the proposed simulation-based bias method. So no statistical difference, as you can visually also see, in terms of task on success. Okay, so they are mostly the same effective both. However, in terms of time, the proposed system was a lot better, required significantly less time and largely less, as you can also see. And there was a very large effect size here, which means that it's not only significant, but also substantial in magnitude finding. No significant difference in terms of perceived usability. Both of them were rated on the approximately on the same 80s on score. So it's this is good to excellent perceived usability according to the literature. And we did find a significant difference in terms of system preference. Significantly more people preferred the simulation-based approach compared to the computer vision-based approach. If we want to quantify it, you can see here we have approximately 5 times more people that preferred the simulation-based approach. In terms of future directions and limitations, we want to investigate the applicability in different type of assembly tasks. For example, tasks that require torque and force or grasping, because this was a simply taken place task, what we monitored. We want to also implement a grasp planning module that's not there currently in the system architecture, and also compare our simulation-based approach against an active, a pure active LFD approach, which is a teleoperation of the robotic system, because currently we compared it only to vision-based, which is a passive LFD approach. So that's all. Here is a summary if you need to remind yourself what we did for your question. And I'm actually a lot earlier by the time. So, okay, 2 minutes at least. Oh, okay. I forgot to start the timer a bit, so it's not 2 minutes.
Few seconds, but it's okay.
Few seconds, okay.
That means you can have another question from the audience and one more. So please, questions.
Thanks for the presentation. If you go to the slide about the comparison of the vision-based and the simulation about effectiveness,
Effectiveness.
Yes.
Yes.
So here there was a significant difference. I think the next one.
It wasn't a significant the effectiveness, efficiency, the time on task.
Efficiency, sorry. Yes, here there's a significant difference. So if I understand correctly, vision-based system is an automated setup. So basically the computer vision system is
it's semi-automated because you also need to start it, evaluate the results. So, but the core is automated as all vision systems.
okay. And here basically the simulated system is user-defined. So the user is active. It's not it's semi-automated, but the user is actually actively working.
Exactly.
Yeah. So it's interesting because maybe in the future we're trying to be more autonomous now, right? So maybe the accuracy of the vision-based system plays a big role here.
Probably.
And who knows, different algorithms or might play a big role into this particular significant difference.
You mean which computer vision system to test, right?
Exactly.
Yeah.
Yeah, because it depends on the algorithm you use there. For the vision system.
Yeah, but we chose one that had chosen the best algorithm for each problem. I mean, in the paper that cited in the literature, they already explored this. So they selected the best with the highest accuracy and stuff like that. Okay. So of course we can take another vision-based system in the future and compare it again. Yeah, fully agree.
Interesting. Yes. Okay. Thank you. Yeah.
In usability metrics, the SUS matrix is at least 20 years old. Do you consider it valid today?
It's actually more than 20, I think. Yeah, and it's I would say it's the most valid instrument currently for perceived usability. For the perceived usability construct particularly. It has been translated in many languages, standardized in various cultures. Yeah.
Okay, thank you.
And there are a lot of benchmark data. You can compare what the quantitative score means, as I already did in my results. For example, this is a data set of 2,000 surveys or something. So this is an interpretation of the number, good to excellent. Thank you very much.